electronegativity is going to be important when we're really focusing in on covalent bonds. It sort of helps explain the differences, the sort of ideas of all the different kinds of bonding from ionic down to covalent, and sort of this range that it's not really just a black and white issue. So officially, it is the ability of an atom within a molecule. So remember, a molecule is a covalently bonded compound. So this is an atom within a compound to attract shared electrons to itself. So remember those shared electrons in the covalent bond, and then we're saying that the two atoms that are in that are bonded together may or may not have the same electronegativity. They may or may not have the same ability to attract the shared electrons to itself. So if one has a higher electronegativity, it can attract the electrons towards it at a greater rate than the one with the lower electronegativity. And that is a pretty complicated way of actually determining it. Linus Pauling came up with this theory, and it's basically measured experimentally. There's a couple of other ways that can be used to measure it. You may see values ranging when you go look it up in different places. It's about the measurement method. However, the big take-home picture is that when two atoms with different electronegativities are bonded together covalently, it's suggesting that those electrons are not shared equally. Here's some values. These are the ones from the book. As you can see, they range. And we saw, remember we talked about the electron affinity and electronegativity trend in the prior chapter, but we didn't really know what electronegativity was. We're starting to get a better idea. But as you see down in the corner in group 1, at the low end of the table, one of the higher periods, francium, is pretty low electronegativity. Of course, we're not going to find it in covalent bonds, really. These are mostly going to be ionic bonds, but we can still measure it. And then we have hydrogen is kind of medium. It's not super high, super low. It's in the middle, but we see mostly our nonmetals. This is where they start to get big, and we see they're increasing towards fluorine. You may notice that fluorine, chlorine, bromine, that's group 17. Group 18 is not shown on here. We don't talk about electronegativity with the noble gases, and that's because they don't covalently bond very often. Not never, but not very often, and so it's not as relative. So fluorine is considered to be the most electronegative atom, and it has an electronegativity of 4. Again, what is going to be most important is going to be relative electronegativity values. When I'm comparing two bonded atoms, are they the same electronegativity or are they very different electronegativities? So one of the problems is that Alex uses slightly different values. So you can get to the electronegativities in Alex when you click on the periodic table and then you click on an element. It will show you things about it, like its atomic weight. And one of the things it lists is electronegativity. Their values in Alex are a little bit different, but they're all consistently different. It may or may not end up showing up where an answer to a question changes based on that. So I'm just kind of putting that out there. I'm going to be looking for cases where I see it's a problem, and I'll warn you if I see that. But just if you get something where like, I know I'm doing it the right way and I'm using the electronegativity values on my test reference table, which is what I'll use in class, if there's a difference, you may see that due to that. So what we really get down to is that there's this spectrum of bond type. It isn't really just covalent ionic. It's very covalent, very ionic, and then a whole lot of in between. So on one end, when we have very different electronegativities, the ability in a covalent bond to pull electrons for the nonmetals is very high, and the metals is very low, such that it doesn't really bond covalently. The nonmetal will rip the electrons away, and we have an ion situation. That's a fully ionic bond, very ionic character. On the other spectrum, if we have two nonmetals that both have strong pulls, they're kind of pulling equally, and if they're pulling equally, that's really covalent. And then we have ones in the middle where we have a high electronegativity nonmetal and a medium electronegativity nonmetal or hydrogen, and they can covalently bond. However, the difference in electronegativity is big enough that one is definitely a stronger pull on the electrons than the other. We would expect in those cases that the shared bond, the shared electrons in the covalent bond aren't in the middle, they aren't in between, they're more towards one of the atoms. And we're going to talk about those as creating polar covalent bonds that are somewhat in between pure covalent and pure ionic. So we will be seeing these in the future. We're going to be looking at some of these cases. It's going to play into something we call polarity. And so let's kind of start with that as we get into more complex Lewis structures. So now we say, okay, so what is the exact cutoff values? So at what cutoff value does it become ionic? Or at what cutoff value does it become polar covalent? And this is very complicated. There's different ways to measure the electronegativity, so that's one problem. Also, chemists don't agree on the exact cutoff values. We know from seeing observations and seeing how molecules behave that some kinds of bonds definitely behave nonpolar, that they are really truly covalent, the electrons are shared fairly equally, and I don't see evidence that it has poles of charge in it. And those would be my nonpolar covalents. So very small differences in electronegativity. So I have two high electronegativity atoms bonded, and what we would say is they compete for electrons equally, which means that the electrons aren't preferentially at one atom, they're like right in the middle, they're shared. And so we wouldn't have any poles of charge. We wouldn't have like more negative on this end, leaving more positive on this end. So there's no dipole, there's no dipole moment. Then we have our medium, this is called our polar covalent. And the polar covalent, we're looking at a medium difference in electronegativity. So it's a high electronegativity and maybe a medium electronegativity. So there's some difference, but it's not so drastic that I have an ionic bond. And these, what we see is that one atom, it's covalently bonded, but one of those atoms pulls the electrons more strongly. That means the electrons are preferentially at that atom or towards that atom, kind of leaving a negative pole, if you will. And then that means if they pull the electron away, then the other atom has a little bit of a positive pole. It's not an ion. It's what we call a pole because it's partial charge. It's not a full negative or a full positive charge. It's just kind of the electrons are distributed and they're more on one atom than the other. So we refer to these things as dipoles, and having a dipole moment is something that we can measure and strengthen with physics and vectors. But you just be able to say that there's going to be like a little bit, almost acting a little bit like it has a negative and a positive side. Kind of like a magnet, but not with north and south magnetic poles, but with positive and negative electrical poles. And again, it's partial, and this is in between range, around 0.5 electronegativity difference up to about 1.7, 1.8 electronegativity difference. So I take the two electronegativities of the atoms that are bonded, I subtract them, and I see how different are they. And if it's medium, we would call it polar covalent. After I exceed some boundary, and again, that boundary is, I don't know, 1.7, 1.8, some people say 2, there's such a difference that we expect that one has such a much stronger pull, it will rip the electron away completely, leaving a formal positive charge and a formal negative charge on another end. So that's an ionic bond. And so these, again, don't get caught up on the exact numbers because it's not going to be consistent. I'm not sure what this book is using, but I think TRO tends to use 0.45 to 2.0. But I haven't double checked in this book. So that's the thing we may see with some of these, classifying it as polar, nonpolar, or ionic.